basically the trophic levels. All right, the organisms are organized in the trophic levels, which we just did, the second trophic level, and so forth. This is a close look on section 5.1, which is about land and marine. Marine is basically oceanic. Whenever you see the word marine, you got to think of, you wouldn't think of like Lake Michigan necessarily, but you would think of the oceans, okay? The Marine Corps, all right? So, that's the idea with that, okay? Real, you can see this closer look provides an opportunity to compare and contrast oceanic and terrestrial food webs. You'll see where the web is not just a straight line of where the food goes, but it could go anywhere. And basically what that means is that this is a nice straight line here, but is it possible for a tertiary consumer, all right, to basically bypass the secondary consumer and sort of consume the primary consumer? Well, yes, it would be. Okay, so the tertiary could consume either one of these. Omnivores could do that. So anyway, we'll look at this. If you get ambitious, I would take a look at this. There's an excellent description on this on the section, chapter 5 on section 5.1. You'll see the section called the closer look. It's pretty cool. Picture's worth a lot of words for that. All right, and a couple more things I want to cover in this video, and then we'll stop. This is about food. Food webs can be very complex, and let's see, several trophic. This should be trophic. Should be an H in there. Okay, trophic levels. Again, you can see this with the picture. We'll go over this later. And then ecosystems as systems. Okay, aspects of residence time. Residence time is just basically how long a maybe a pollutant, for example, stays in flow to the lake and stuff. The rate of flow to the lake, the size of the lake, and the rate of outflow. All right. A couple things I want to talk about here. I'm going to go down at this point, discuss these, and this will conclude the first tape on first video on ecosystems. But basically, so a lot of this should be somewhat familiar. Now, I know there's a couple of new terms here. Let's look at the familiar part. This should be familiar. This is probably newer here, at least the way it's put. Okay, maybe the idea makes sense. Energy is defined as the ability to do work. And work can be defined as the movement. You can see energy is difficult. It's not something we tangibly hold. We can hold matter that has energy in it. But energy can be kinetic or potential, moving and non-moving. And there's different types of energy, heat, light, and chemical. And we'll see that energy is conserved. We'll actually see this a little bit later on. All right, energy is actually conserved, meaning it's never created nor destroyed. All right, now a couple of new terms. Energy flows from the external environment through ecosystems. That through is a good word there to remember. And from one organism to another and back to the external environment. The ecosystem is an intermediate system. That's one new term. Between the energy source and the energy sink. So basically you've got the sun. All right, you've got the ecosystem, which is your intermediate system, I should say. And you've got the energy sink. Just think of a sink at home, you dump things in the sink. All right, basically kind of a catch-all for everything. Energy that enters an ecosystem is photosynthesis or chemosynthesis, moves along food chains until it's temporarily stored in net production or dissipated as heat. All right. Storage would be like in plants and stuff like that. I'll get into net production in just a little bit on the next video. While the material building blocks of life are recycled, energy doesn't recycle. We talked about that earlier. It flows in as light energy and out as heat. The flow of energy powers, this is a big one, the flow of energy powers the biogeochemical cycles. So sometimes we're asked, what is the power behind the water cycle, the hydrologic cycle? And the answer is the sun. All right, last two, first and second laws of thermodynamics. This is the one where the first one is energy is never created nor destroyed, it's only changed in form. Something I want to talk about here is usable energy versus non-usable. All right, usable versus non-usable energy. Usable would be, for example, the gasoline in my tank of my car. That's usable energy. The non-usable would be the CO2, water, that it basically combusts to as it goes out to the atmosphere. So the first law is that energy is never created nor destroyed. It's only changed, transformed. Okay. And the second law of thermodynamics basically states that any conversion of energy from one form to another, some of the initial energy input is always degraded into another form. So in other words, to change energy, basically costs energy. You've heard the expression, there is no free lunch, meaning we have to pay for everything. And this basically is true with energy. In order to change from one form of energy to another, it costs you energy. This is called the law of entropy. All right, order requires energy, and the second law of thermodynamics predicts the level of disorder, which is entropy in the system. A simple demonstration is disorder occupants fail to invest the energy necessary to maintain order. Energy exists only by increasing the disorder, the entropy of the entire system by converting high-quality condensed energy to low-quality dispersed energy. Anyway, we'll stop there. I appreciate this. Take a look at this weekend. You can use your notes on the quiz. Thank you very much.